Welcome to another video for Stat 212. So today in this video we're going to talk about visualizing distributions and specifically distributions for numeric data. So I am just going to pull the notes up. So there's lots of ways that we can visualize our data. Here we're just going to focus on what we call univariate representations, meaning just representing one variable at a time. So if we're working with a numeric variable, histograms would be a very common representation that we could create to just very quickly see how our variable is distributed. So here we have the heart rate data for the class from a previous semester. And so we can see that, we could see before kind of our range of data, but the histogram really helps us see how often we see certain responses, and that most responses are kind of in this middle area, right? So if I just kind of highlight right around here, so most of the class seems to be between about, we'll say about 60 and maybe about kind of 80, 85. And then after that, we see a real drop off there and how many folks have heart rates beyond those limits. So obviously, we have heart rates, across a pretty large range, but the histograms kind of help us see the shape of our variable here. A density curve is another representation that's, essentially the same thing as a histogram. The only difference is that we're just smoothing out the edges. So this is something that we would commonly do if we're trying to represent maybe like the population or represent kind of a large amount of data. So like this is kind of the trend that we see in this variable. We see kind of this, big peak followed by some kind of decline, maybe a slightly right skewed distribution, as we'll define in just a second, but definitely kind of this one pronounced peak with fewer and fewer observations going on either side. So density curves are often what we do for kind of approximating what's probably going on in the population, or if we just have a lot of data such that we feel, that we can just go ahead and represent without the bars because we have so much. One other thing I'll mention about histograms is kind of choosing a bin size. So when we get to using R, we'll talk a little bit about creating histograms, and you can choose how many bins you would like to use in your histogram, and usually the default in R would be 30. But a lot of times it's better to actually go with fewer bins. So I think here this is probably around 20 to 25. So there's not really a correct answer for choosing, how many bins you want and how wide these bins should be. But usually one thing that I like to say is that you don't want a bunch of unnecessary gaps like within your data. So if you have so many bins that you just have like nothing, in several places kind of throughout the core of your data, then you probably have too many bins. But you also want enough bins so you can kind of see some shape. Because if I just used maybe like 4 or 5 bins, I wouldn't get the same information. Like I wouldn't have as much of a clear picture what's going on. So I'll just kind of mention that in passing. All right, so there's different terms that we can use to describe the shape of a distribution. So one thing that we can kind of notice is symmetry versus skewness. So symmetry would be when our distribution is kind of, we could kind of draw a line and say that the distribution is pretty symmetric about that line. So this histogram over here, or the density curve, either one, are almost symmetric, but not quite. Like I could draw a line through the sort of middle, and I would get a little bit of symmetry here, but at least with this data, it's a little bit, a little bit more data kind of stretching out this way, but it's almost symmetric. So all these are different examples of what symmetric distributions could look like. One is just kind of this one peak, this one mode, as we'll call. Here is a 2-peak or 2-modal bimodal distribution. And then here we have a uniform distribution. So all these are examples of symmetric distributions of different kind of different shapes. So when our data is not symmetric, then oftentimes it means that it's probably skewed, meaning that more data is concentrated on one side with data kind of skewed out towards the other direction. So here we have data that's mostly concentrated on the right, on the positive, or the more positive side, and the skew is kind of stretching out negatively, Or oftentimes we won't say negative skew, we might say left skewed. So I would just kind of be familiar with both of these terms. And here's an example on the right where most of the data is concentrated on the left, and the skewness is kind of pointing in the positive direction, or towards the right. So in both of these cases, the data is not symmetric. Oftentimes when we look at skewed data, or we see skewed data, it means that there's kind of a hard floor or a hard ceiling, meaning that you just, like, it's impossible to have data points beyond this value. Oftentimes with left skewed data, that floor might be something like 0 if you're measuring something where the value can't be below 0, like a height or something like that. You might see kind of data clustered towards the left side, and then it's kind of stretching out, or, well, I don't know which way my camera is facing. Stretching out, I guess I'm pointing left, but in the video I'm pointing right, where it's, you have 0, you have data clustered, and then it kind of stretches out, skews out to the right. So that's often the case, or often something that happens when we have skewed data. All right. So the mode is a term that I just mentioned, and that just refers to kind of the most common point or a peak that we see in our distribution. The heart rate data, we had one mode, it was unimodal. And here we have another example, another data distribution where it looks like this is more bimodal, where we kind of have one peak over here, one mode here, and then we have another mode kind of right around here. So this would be bimodal. Whereas over here, this one looks a little bit more unimodal, right? We don't have any other kind of clear peaks emerging. And it's a little bit subjective, right? Because, what happens if I have like a little, what if I have like a little bit of a bump over here? Is that a second mode or not? And so, it gets a little bit subjective deciding that. But usually if we have kind of this clear, pronounced peak in multiple places, we would call each of them modes. And that helps us kind of understand what's going on in our data. So here, this represents the petal length of a sample of iris plants. And one thing that I notice here is that we have a really big discrepancy here between this group and that group, right? So it's like, well, why do we have this big gap? And then all of a sudden we have a bunch of plants with petal lengths here and then petal lengths here, because I would expect it to be a little bit more kind of continuous here. So the answer is, with this data set, that there's actually more than one species involved in the measurement. In fact, I think there's actually 3 different iris species in this sample. And one of them is represented right here, where this species has much smaller petal lengths, and the other 2 are represented over here, where they have much larger petal lengths in comparison. So noting things like that can kind of help us understand what's going on in our data and prompt us to ask questions and look at our data more carefully to see, why the observation we're seeing, how that kind of plays out in the context of how the data was collected and what it represents. Box plots are another really helpful measure, especially for looking at either one variable, like one numeric variable, or even looking at and comparing multiple groups, as we'll certainly do later in the class, where maybe we have like side-by-side box plots of 3 different groups and comparing one, the same numeric variable for these multiple different groups. So a box plot is basically representing the 5-number summary. So if you remember the 5-number summary, that's going to be the minimum, the first quartile, second quartile, third quartile, and the maximum data point. So what we can do here is represent each of these elements of the 5-number summary with a horizontal line, and apply it next to a numeric scale, and we can very quickly visualize kind of the distribution beyond just looking at the numbers listed out, right? So I can always look at the 5-number summary, and that's helpful, but visualizing the 5-number summary on a graph, might be a little bit more helpful. So one thing to note, though, about box plots is representing what we call extreme values, or you might call them outliers. And that is when we have data points that are kind of abnormally far from the rest of the data. And so box plots, usually represent those as dots outside the highest or the lowest whisker. So here we have 2 data points in the heart rate data that are so far away that we want to note them separately. So in that case, when that happens, the highest line here is no longer representing the maximum data point. It's representing the maximum data point that wasn't labeled as an extreme value. So how do we decide if something is extreme value? Like, is this just subjective, or is there some kind of process for making that decision? And so the answer is kind of both. There is some subjective decision making when it comes to identifying data points as maybe being outliers that we should exclude from analysis. But there is kind of an objective measure that you could use to help you decide that, if you maybe have to help you kind of decide on some candidates that you should consider removing. And that would be the upper and lower fences. So these calculations are shown here, and we can use them to find extreme values from the heart rate data or from this test score data as well. So we're going to practice here with the test score data. And you might remember that the 5-number summary was 24, 80, let's see, I think it was it 90? I have to, I'm going to have to do this all over again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think it was 89. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so, and then 94, yeah. I think that's how it worked. Yeah. Okay. So here's our 5-number summary of the test score data. Are there any outliers in this data set? So the lower fence is going to be the first quartile minus 1.5 times the interquartile range. So in other words, we're starting at the lowest quartile and then saying, okay, let's stretch out 1.5 of our interquartile range. And if we have any data points that are farther away than that, then maybe that's kind of a candidate to be called an extreme value, because that's pretty far away from where most of the data seems to be. Okay, so the lower fence here is going to be our first quartile, 80, minus 1.5 times the interquartile range, which is going to be 94 minus 80, which is just 14. So this is going to end up being 80 minus 21, and that's going to be 59. All right, so as you might notice, 24 is our data point that is below 59. We have one data point below 59, so this means 24 is an extreme value. It's unusually far away from the rest of our data. All right, so the upper fence is going to be our third quartile, 94, plus 1.5 times the interquartile range. So it's going to be 94 plus 21. And that's going to be 115. And you'll notice that we don't have any data points above 115. So that means we don't have any extreme values on the higher end of our data. So no extremes on higher end. Right, and so there's, this is a very objective procedure, right? So we just kind of calculated that these are some unusual data points with respect to the distribution of our data. And what they really tell us is we should pay attention to these values that are kind of outside the fences. That means that they are, numerically unusual in our data set. It doesn't necessarily mean that we just throw them out and we pretend like they don't exist. That would be a more contextual question. That just depends on what we're doing and just how far away it seems to be. But this is a nice thing to kind of highlight values that we should consider for removal, or question what happened with these data values and why they're so unusually far from the others. Okay, so just keep in mind, this is going to be a lot, really relevant when we're graphing data and, we have some unusual extreme values. We're going to see lots of data points that are really unusual, and that make it hard to see what's going on with the rest of our data because our scale has to be stretched out so far to see some of these extreme values, right? Like if I make a box plot and most of the data is in this one little sector, but then I have a bunch of data points way up here, it really crunches down, my visualization of most of the data. So it's really common practice when we're visualizing data to just filter out values that otherwise make our graphs kind of hard to read. And right, that doesn't necessarily mean we're just removing them from analysis. It means that we're moving them out temporarily for visualization purposes. However, when it comes to like formal analysis, like running, we'll run things like a hypothesis test. We don't necessarily need to remove values there unless we just think the value is a mistake, or we think the value, like there's just something wrong or anomalous about how this value was collected. So we can be a little bit pickier about removal for testing, but we can be very generous about removal for visualization purposes, because that's a more, that's just to help us kind of see what's going on. All right, kind of in the spirit of removal, here's a good contextual question to kind of dig into. So in a previous semester, I asked students how much money they expected to make 15 years from now. Some extreme values that didn't pass the upper-lower fence criteria included $8,000, $500,000, $750,000, $2 million, and some very large 9 quadrillion number. Which of these might be considered outliers that we should just throw out altogether? Okay, so right now keep in mind all of these failed the fence criteria. All of these are outside our fences. So that's kind of our objective starting point, which means that's why we're looking at them. That's why we're asking about them. So now we're asking kind of the next logical question. Are any of these just, would it make sense to just, remove them completely? Or are they still sensible values that maybe we should retain in our data set? Right, so think about some things down here. Is it a measurement error? Is it a non-serious answer? Is there something different about this observation that we should examine? And I think there's a couple things that we can point out. So when I look at these, I feel like 500,000, 750,000 are still very sensible answers that I could see somebody saying, right? Like those are not, like they're very high, but they're not outrageous salary values. 2 million's a little bit more questionable, but again, like it's not outrageous. It's, I would say it's still borderline reasonable. Now, I don't know about you, but I think that 8,000 doesn't make a lot of sense. 8,000 seems like maybe a mistake. Maybe this person read this as monthly income instead of yearly income. So that makes me think that this doesn't make a lot of sense. Like it doesn't seem like a very reasonable answer to this question, especially for a college-educated student to say for their yearly income. 8,000. And now I don't fully know why, this answer came. I have a suspicion that it's a misunderstanding of yearly versus monthly. But I do know that it doesn't make a lot of sense. And definitely this, this 9 whatever value, this is just not a serious answer, right? Like maybe this person does think they're going to make a lot of money. I don't think they really think they're going to make that much money, or something is terribly wrong if they do. But I'm just going to say it's not a serious answer. And so I don't want to necessarily keep these in my data when I'm doing like a formal analysis, like a hypothesis test or something like that, where all the values count. So those are values that I probably feel better just removing completely. And the other ones I think I'm okay keeping. I have some flexibility when it comes to visualization. Like, if this 2 million value is just too far away and it's making it hard for me to see the distribution of my other data that's mostly between, like, say, 75,000 and 250,000, if that's where most of the class is, and then I have 2 million, well, this is going to get squeezed down like this when I'm trying to make, a box plot or a histogram. So 2 million is something I could certainly remove for visualization purposes, but I don't necessarily want to remove it from analysis because I think it's still a reasonable answer. All right, So we're going to pause our video there.